All right. Hello, BC Calc. How are you? Let's start with today. Hope you're all enjoying this just completely daffy school off day. Um, Okay, this was one of your homework questions from last night. Just wanted to go over. I just picked one that I thought would be the most compelling. I could be wrong. If there are any questions that remain, we can ask tomorrow. So this was question, I don't remember one of the questions, but you can go ahead and find it. To find the Maclaurin for y equals e to the x squared, determine the radius of convergence. Using shortcuts, we know, and this is hopefully you have these committed to memory on some capacity, e to the x is this Maclaurin. By a substitution, e to the x squared is here. Notice what I did was I did write the general term. Remember, when you write the general term, you always also want to make sure you state where n begins. And the question was asking for the radius of convergence. I just changed to k's here for no particular reason. Ratio test for absolute convergence. When you simplify the limit argument, we are here. As k approaches positive infinity, this limit will always equal 0, which is always less than 1. So the interval of convergence is negative infinity. So the length, if you will, of half of this interval is positive infinity. Kind of a daffy idea. Okay? All right, let's now do this. Would you please go and find the Maclaurin for e to the ix? E to the ix. Okay, we can do it together. You know, we know this is e to the x here. E to the ix is right there. Would you agree? There it is. Now what I'm going to do is do some simplifying because I know I raised to powers. I'm going to ask you to ignore these color-coded dashes in 1 second, but you know, I squared here is -1, right? So that's how this term right here becomes -1x squared over 2 factorial. Similarly, I cubed becomes -I x cubed 3 factorial. I to the fourth is just +1 x to the fourth factorial. And I went ahead and did a few terms out because I want to show you something. This is pretty magical, I have to say, and part of me wants to tell you this too. If this doesn't kind of blow your mind, I don't know. I just think you're all far too young to be, you know, not receptive to just pure mathematical beauty when it happens. I want you to notice something. The yellow terms, if I just collect the yellow terms together, the yellow terms are the Maclaurin for cos x. Okay. The green terms, if I factor an I out of each of the green terms, the green terms give me I sine x. Okay? So what that then tells you, and again, I really hope that I hope there is some joy that you feel here. What that tells you is that e to the ix actually equals cos x plus I sine x. Now, this equation right here is one of the most famous in the history of mathematics. It's called Euler's principle. You don't have to know the name. In fact, this is just, once you get into the world of Taylor series and you get through all the grunt work of convergences and convergence tests and intervals of convergence, there's some pretty amazing things that can happen. This is Euler's principle. And what Euler's principle tells you is a number of amazing things. I'm just going to show you one of them. If e to the ix equals cos x plus I sine x, then e to the power of I times pi, right, if x equals pi, should equal cosine of pi, which is -1, plus sine of pi, which is 0. So e to the power of I pi equals -1. I hope that there's this moment where you gasped, because look at this. This is unbelievable. The transcendental number e raised to a power that is a product of another transcendental number and an imaginary number gives us a real number, -1. It's just amazing, isn't it? Absolutely amazing, right? And there are a whole bunch of things that you can kind of play around with this. I mean, this gives you some incredible things like e to the I times pi over 2, for example, is going to equal 0 plus I, or e to the I times pi over 2 equals I. This one's pretty cool too, but I really think if I were to make a t-shirt and, you know, put a logo on the front, this is pretty mind-blowing. Like, this one disturbs people greatly, and for that reason alone, it's just wonderful. But I digress. Let's keep going, okay? Let's talk about, again, we're kind of in the latter part of working with Maclaurin and Taylor series, or Taylor series to capture them both in one sentence. Let's take a look at the radius of convergence for f of x equals 2x sine x, okay? Now, we're going to use our shortcuts here, and I should tell you too, by the way, that the shortcut questions, you know, where you're asked to generate a series for a particular function where you can use shortcuts, they almost always pertain to Maclaurins. In fact, I'm trying to reach back in my archives here and think to myself, have I ever seen one that involves Taylor? I mean, I guess if I really go back and look and think about it, I probably could find one, but generally speaking, these questions that involve shortcuts to find a particular series, they often, almost always, involve Maclaurin series. Now, in this case, this is a shortcut that I don't think we've used it yet, or maybe we have, I actually can't remember, but I'm asking you to find the Maclaurin for 2x sine x, and what you can do here is none other than generate the Maclaurin for sine x, and then really, as you see here, 2x sine x just means multiplying each term in the Maclaurin for sine x by 2x. And just be very careful of just the way the powers of x modify, right? So here's your Maclaurin for 2x sine x, and you'll notice over here as well, I put the general term, and again, please be really mindful of the general term, how you kind of cobble it together, and remember, make sure you state where n starts. And then if I were going to write this in summation notation, I'm right here, and I just kept this in terms of n, okay? And now we're looking at, oops, I just lost a factorial here for some reason. Very good. All right, now I want you to find the radius of convergence for this particular Maclaurin series or Taylor series about x equals 0. Go ahead and find that and replay me. And when you find that, here we go. This is the ratio tests for absolute convergence. I showed here where the 2's cancel. This is the simplification. Kate Hart, I'm thinking about you right now. When you simplify, you know, a quotient of factorials, how are you doing with those? Please let me know. This is the remaining of the factorials after you simplify. This is the entire argument of the limit. As n approaches positive infinity, the denominator approaches positive infinity, so the whole thing approaches 0, which is less than 1. So the radius of convergence is positive infinity, okay? All right, so when you have these screencasts, it's, of course, obviously I'm not in there in your house with you, but the places where I do say to pause and practice this, if you are not doing that, I think you're kind of shortchanging yourself. So just food for thought, all right? Another shortcut. So let me give you another shortcut, and this is the final one we'll do here. The final shortcut is this one. You know, the shortcuts we've seen so far have to do with like your homework last night. You know, if you're asked to find the Maclaurin for e to the x squared, one shortcut involves changing the input value, which means just modifying the input x, right? So if you look at the Maclaurin from e to the x to e to the x squared, it's about inputting something in the place of x. Another shortcut that's very common is this one, when you are asked to find the Maclaurin for something, some factor times a function whose Maclaurin that you know, then what's happening here is you're saying multiply 2x times each term in a Maclaurin, right? Those are two shortcuts. And here is the third that you're going to want to know. Let's say we wanted you to find the Maclaurin for this function, e to the x cosine x. Okay, so the Maclaurin for e to the x times cosine x, in this case, what we're doing is we have a function that is a product of two functions, both of whom's Maclaurins we know. So what I'm saying here is we know the Maclaurin for e to the x is none other than this. Okay, we know the Maclaurin for cosine x is none other than this. Okay, if you are asked to find the Maclaurin for e to the x cos x, what you can simply do is multiply the Maclaurin of e to the x with the Maclaurin of cosine x. And that may sound incredibly intimidating and arduous, but it really isn't. So just watch me for a second. Let me do a setup. And you'll see how we do this, okay? Let's write it out first. Okay, Walter, did you get the notes that you needed from radius of convergence? I just noticed a righto over here. Goodness. It's the 4th over 4 factorial minus x to the, oh goodness, look what I did. I skipped over here too. Good gracious. X to the 6th over 6 factorial. X to the 6 over 6 factorial. All right. So here's the thing. When you have a question like this that requires you to find the Maclaurin of a product of two non-polynomial functions, right? E to the x is a transcendental function. Cos x is a transcendental function. Transcendental functions are nothing other than, for our intents and purposes, non-polynomial functions. As you'll notice, all the Taylor series we found, they are most conveniently ordered in this standard form where the terms increase by degree, right? Degree 0, degree 1, degree 2, degree 3, degree 0, degree 2, degree 4, all right? So it's most helpful when we are looking at a Maclaurin for something potentially arduous like this, that involves multiplying two polynomials. Here's what I recommend that you do. You start with looking at these terms and you ask yourself, how could I have constants? Because I want to start and check if there are constants. Then I want to check if there's a degree 1 term, then degree 2, then the degree 3. So for constants, I recognize that I can get a constant by saying 1 times 1. Over here, right? 1 in the first polynomial times 1 in the second polynomial. There is no other way I can get a constant. You know, there's nothing like, there's like if I say 1 times 1, when I do the distribution, for example, 1 times 1, then 1 times negative x squared over 2 factorial, then 1 times x to the 4th over 4 factorial, right? Or if I distribute this way, 1 times 1, or 1 times positive x, or 1 times x squared over 2 factorial, the only way I'm going to get a constant is by multiplying this term times this term. So I know my constant term in the Maclaurin that is my goal is just going to be 1. Okay, I'm going to erase this so we just don't get lost in my next notations. Now the question is, how do I get any degree 1 terms? All right, I'll just put a plus sign here, and I know that this sign could always change. Well, let's see. When it comes to degree 1 terms, I could get a degree 1 term by saying 1 times positive x, agreed, and is there any other way that I can get a degree 1 term? Let's see. 1 times positive x, well, that's the same thing as positive x times 1. There is no other way I can get a degree 1 term. So this is going to be plus x here. Okay, let's look at the degree 2 term. Now this gets a little bit more interesting. Well, let's see. I can get a degree 2 term by looking at positive 1 times this term, negative x squared over 2 factorial. Write that down, negative x squared over 2 factorial. I could also get a positive 2 term by doing positive 1 in this polynomial times this term, right? So I'm going to do that here plus x squared over 2 factorial. Now I look back and I ask myself, there's an x here, but there is no x to the power of 1 in this polynomial. So when it comes to distributing this term x, I'm not going to get a degree 2 term in any other way other than these two, right? We're going to clean up in just a second, so just hold on a minute. All right, let's go to now the degree 3 term. Okay, so it's all about just looking at the ways this distribution, granted it's going to be a horrific FOIL to use the acronym that you may have picked up way back in the day, but it's about just savvily working your way up in degree. All right, degree 3, well, let's see. One way I can get a degree 3 is by doing positive x here times this x squared there. So I'm going to write this down, negative x cubed over 2 factorial. All right, the other way I can get a degree 3 term is by doing x to the cubed here times positive 1, right? So this gives me plus x cubed over 3 factorial. And is there any other way that you can see that I can get a degree 3 term? I'm taking a look. There's no degree 1 term here, no degree 3 term, so degree 2, degree 1, degree, I wish there was a degree 1 term in this one, because then I could have done x squared times the degree 1 term here. But nope, nope, and nope. I think that's it, isn't it? That's it. Okay, so then what we've got, let's keep going on. The next one's gonna be degree 4. Okay, degree 4, I'm just gonna erase these markings just so we don't get crazy. Degree 4, let's see. I get a degree 4 by doing x to the 4th times 1. I also get a degree 4 by doing x squared times x squared. I get a degree 4 by doing... Is that it? It's just, I thought this was going to be a little bit more fun. Goodness. X cubed, x... That's it. All right, well, this becomes, let's see... minus x to the 4th over 2 factorial times 2 factorial. And then the reds here, it was plus x to the 4th over 4 factorial. Okay, I'm just double checking to make sure that there is no other way that I could have gotten x to the 4th. X to the 4th, no, no, oh goodness gracious, okay. Oh no, there is one right here, I just missed it, look at this, silly me. Goodness, I bet one of you was like, right here. Yes, Nancy, I found it. Don't worry. That was plus x to the 4th over 4 factorial. There's a factorial here. Okay, and then there's no other way that I can get degree 4 term, is there? No, there's not. All right, and then now something interesting happens. If you look here for a minute, this becomes, well, these cancel out, right? And my Maclaurin becomes 1 plus x minus x cubed over 2 factorial plus x cubed over 3 factorial. And these I'm going to simplify, but I'm not going to knock myself out here. This is minus x to the 4th over 2 factorial times 2 factorial is just 4. And then this becomes plus 2x to the 4th over 4 factorial, okay? Because again, just watch your work with fractions. A lot of times in these kinds of questions where you're asked to find the Maclaurin for a function that requires multiplying 2 Maclaurins, rarely is there a pattern that is particularly useful, okay? Oftentimes the question will say something like, find the first 4 non-zero terms. Now here is where you have to be very, 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 very careful. In a Maclaurin series, right? Each degree indicates the power. So this is 1 term, this is 1 term, but look, the degree 3 term is the sum of those two. The degree 4 term is the sum of those two. If I were to make this even more explicit, you would want to, if you want to make sure that you don't forget that, you can get yourself into the habit of just combining like terms. However, when you combine like terms, you need to make sure you embrace your inner love for fractions, Paige. Yes, Paige. Paige loves fractions, and that is completely and totally not true. All right, but you've got to just, at this point, make sure that you take it all the way and embrace your love of fractions. I'm going to do a ... here, so I just signify to the reader this does go on forever. 1 plus x, now this becomes over here, right? 3x cubed over 6, so this becomes plus, right? Negative 3/6 plus 1/6 is just going to be 2/6 or 1/3. X cubed over 3. This becomes negative, what is this? Negative 3/12 plus 1/12 becomes negative 2/12, which is negative 1/6. So negative x to the 4th over 6. ... Okay, so now what I've done, more often than not, questions like this will say, find the first 4 non-zero terms of the Maclaurin. What they're checking here is your use of polynomial multiplication and your use of savvy polynomial multiplication. Checking just your use of attention to detail, your use of just very detailed math, right? Now, once you're here, remember, this is an approximation for the function e to the x cos x, wasn't it? Right? And I'm going to do this. If I go like this, I use an approximation. I'm just going to write the first 4 non-zero terms out. And if they just want the first 4 non-zero, I actually don't have to put any ... here. All right, everybody. Well, now I'm going to ask you these questions. If f of x equals e to the x cos x is approximated by this degree 4 polynomial, would you please then go and find f of 0, f double prime of 0, and f triple prime of 0? Okay, and please do that with me being paused. F triple prime of 0. What do those things equal? And come back and replay me. All right, well, f of 0 is just 1, right here. F double prime of 0, there is no degree term in this Maclaurin, so f double is 0. F triple of 0, we know the third derivative at 0 is going to be somewhere in the coefficient of the degree 3 term. But remember, in general, the degree 3 term for a Maclaurin looks like this, right? Sometimes, though, Maclaurin series will have it simplified, as it is here. Okay, and if you look at this is the actual term, my Maclaurin. The question is, and obviously the x cubes cancel, f triple prime of 0 is going to equal 3 factorial all over 3, or just what number? Yes, 2. So f triple of 0 equals 2. All right, so tonight's homework is going to be detailed. What I'm going to put on the teacher page is amended instructions, where I think some of the questions just ask you to find the first 4 non-zero terms of the Maclaurin here, of some product of functions. I'm going to probably add to that. All right, let's close out now with this question. There we go. All right. Would you please go ahead right here, find the interval of convergence of this function by way of generating the Maclaurin series for this function and determining the interval of convergence. Okay, so first step, please find the Maclaurin series for this function and then find the interval of convergence and then replay me for the answer. Oh, bloody hell. Okay, got it. Well, here we go. Here's some work. Here is me just computing my necessary pieces of information. F prime, f double, f triple, f the 4th deriv. I plugged in my 0 values to get my values here. Here is me composing the Maclaurin for this particular function. Pardon me, I had to put a ... This is me just composing the Maclaurin. And because I did see a pattern evolve here, I did go ahead and simplify and cleaned up. And when you simplify and clean up, look at this lovely Maclaurin here. Notice my finding the nth term and showing that the nth term starts integrally for n is greater than or equal to 0. And then the question regarding the interval of convergence, I set up this Maclaurin series in summation notation, use the ratio test for absolute convergence. I want the absolute value of x to be less than 1. So -1 to x to +1 is the preliminary interval of convergence. And then here I was able to just see it fairly quickly. When you plug in -1 for x or +1 for x, right? Well, let's just break it down. If you plug in +1 for x, this becomes a summation of 1. So this series is 1 plus 1 plus 1 plus 1 plus 1. Obviously, that diverges by the divergence test. When you plug in -1 for x, that's going to diverge by the AST. So what I have here at the end of the day is IOC is x is from -1 to 1, not inclusive. All right, part B is where things get a little bit juicy. Part B just is this question, and I actually pulled this from your text, but the way they lead you here, I don't think is particularly satisfactory, but let's neither here nor there. The question says, show that this sum equals this based on your work above. All right. Really what they're asking you to do is to use the Maclaurin you found for 1 over 1 minus x to generate a Maclaurin for x over 1 minus x squared. Okay. Once you do that, there will be a link here. Well, let's just break this down. So let's make sure we understand algebraically, how do we get from this to this? Okay, what things happen algebraically? Well, the first thing that happens is you would, let me back up. Many would say, oh, the first thing you do is I want to take this Maclaurin here and multiply it by x, because that will give me then x over 1 minus x, right? And that is a true statement. The problem, though, is there's nothing you can do to this in a clean way to then get you to the denominator only being squared and not the numerator, correct? So let's regroup. If I start with the Maclaurin for 1 over 1 minus x, and if I multiply this by the Maclaurin of 1 over 1 minus x, right? This will then give me 1 squared, which is just 1 over 1 minus x squared. So if I generate the Maclaurin for this first by multiplying the two Maclaurins for these two, that will get me halfway there. Once I have the Maclaurin for this series, I want to get to here. That's where I would say, okay, let's take the Maclaurin of 1 over 1 minus x squared and do this to it. Multiply each term by x. You understand? All right. Now go ahead and try this. See if you can do it on your own with savvy choices of multiplication. And by savvy, we're defining that as aggregating terms by increasing order of degree. And then please replay me, but please, please try this on your own. All right, where did my solutions go? Let's see, I'm gonna find them. Where did they go? Okay, where are they? All right, here we go. So the first step here is acknowledging the Maclaurin from our work above, right? Then I want to take 1 over 1 minus x and multiply it by 1 over 1 minus x. That will get me here. Here is 1 over 1 minus x times 1 over 1 minus x. And here is where you're going to start the multiplication, right? You want to start by asking yourself which distributions from left to right or from right to left give you constants. And here is me breaking that out. Do you see that? Let me elucidate the work right here. So the way I got 1 is pretty self-explanatory. You only get a constant by doing 1 times 1, okay? You can get a linear term by 2 ways. You can go x times 1 this way, or you can do x times 1 that way, but that's it. All right, x squared, that's pretty interesting. How do I get x squared? Well, you can get x squared by going, oh no, x times x this way, 1 times x squared this way, or 1 times x squared this way. That's why there are 3 ways to get x squared, right? And then here's x cubed, da 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 da. And then what you see here is, I just took it out to, I think, the 3rd degree terms. And here is my constant, degree 1, degree 2, degree 3. This here is the Maclaurin for 1 over 1 minus x squared. But that's not my final stop. My final stop is to get here. And this is taking the Maclaurin above here, multiplying every term by x. Be careful. And then you're here. Boink, 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 boink. And you'll notice that if I take this Maclaurin and express in summation notation, I get this. Fantastic. Okay, so what I'm going to do is post your homework on the teacher page, but this is classwork and homework, hence the long screencast here. I trust that you will do your due diligence, and I look forward to seeing you tomorrow, 2nd period. We have a quiz tomorrow. I told you it's going to be on 2 topics, Taylor series. Anything involving Taylor series, of course, obviously nothing that was new presented today, or related rates. Quiz is going to be half multiple choice, half free response. Hopefully, Jason and Nancy, you remembered what in the world related rates were. Yeah, related rates. Okay. All right, everybody, have a great day, and I hope that you enjoyed your day off. Goodbye.